Thinking about electromagnetic induction, let's go back and remind ourselves about the three devices that we looked at GCSE, which involved electromagnetic induction: the generator, the dynamo, and the transformer. Now, we're only actually going to go back and look at the transformer in detail at A level, but all of these we talked about the change in the magnetic field through the coil, or we talked about cutting field lines. Now, that was all very well, but we now need to talk about this in terms of the rate of change of flux linkage with our conductor or coil. So that means we have to define what we mean by flux linkage. If you think about the flux field lines through a coil, let's say this coil has a single turn. So there you have the flux through that turn. If that has an area A and this has a flux density B, your flux linkage phi through that turn is B times A. Now, we know if this was the coil of a generator or a dynamo or indeed a transformer, that if we were to double the number of turns in our coil, that would change the induced potential difference. We would have called it at GCSE. We're going to call it EMF at A level. The induced EMF would double. And if we were to triple the number of turns, we would triple the induced EMF. You remember the things that affected the induced potential difference across our coil was the number of turns in the coil, the cross-sectional area of the coil, the speed of turning of the coil, and of course the flux density. Now all of these, the strength of the magnetic field we would have called it, all of these contribute to changing the flux linkage. So phi is BA, flux linkage is BAN, so flux linkage is N phi, which is BAN. So flux linkage, the total flux through the coil, equals N phi equals BAN. As we said before, phi is BA, flux linkage. The total flux through the coil of N turns is BAN, flux linkage is N phi. So, the flux linkage with a single turn of wire B times A. Flux linkage with N turns, B, A, N. What about if we have a coil at an angle other than 90 degrees? So here we have our coil of n turns. We have our field, flux density B, running through, and there is an angle. Here we have a normal to the coil at right angles to the coil, of course, and there's an angle theta between the field and that normal. So we need to know the component of the field at right angles to the coil. We know the component horizontal, parallel to the coil, I should say. We know the parallel component has no effect, but the vertical component, that is to say the component at right angles to the coil, does have. So if we resolve our field at 90 degrees to the coil, that would be B cos theta, which leads us to our flux linkage being B A N cos theta, or B cos theta times A times N, remembering that this is a cross-sectional area A, this is N turns, and we have a flux density B. So there we have our flux linkage for our coil at right angles, at some angle theta to the field. Now let's look at the laws that pertain to electromagnetic induction. So there are two laws that we need to consider, need to know about. We have Faraday's law of electromagnetic induction, and this is something we have already kind of touched on. The induced EMF across the terminals of a coil, across a conductor, I'm going to say, is proportional to the rate of change of flux linkage. That is to say, the induced EMF is proportional to the rate of change of flux linkage. Now, if you're a mathematician, you have the expression for the rate of change, for the flux linkage, BAN cos theta, and it may well be that you've done the differentiation of cos theta, and what you find is that your induced EMF is equal to minus BAN sin theta, differentiation of cos theta, omega t you would have in here, of course, is minus sine BAN omega, sine omega t. So your induced EMF I'm going to put that all into a rather better state. cos omega t, where omega, of course, is your angular speed, and t is your time, and the angle swept out, of course, is omega t. This is radians per second, this is seconds, so your radians is omega t. We talked about this with circular motion. If you differentiate cos omega t, you get BAN omega sine omega t minus BAN omega sine omega t. So that is what Faraday said. The induced EMF is proportional to the rate of change of flux linkage. Now, what Lenz said, he's our next man, what Lenz said is that the induced EMF happens in such a way as to oppose the change causing it. Now, if you remember the equation that we had our induced EMF is minus BAN omega sine omega t. That is really what Lenz said. And this bit, if I can manage to do it, this bit is what Faraday said. So our induced EMF is proportional to the rate of change of flux linkage, and it always acts in such a way as to oppose the change causing it. Now, there's an obvious conservation of energy point in this. If you think about a coil of wire sitting between the poles of a magnet, and I won't draw any more bits, but I put current through here. Now we know that we have a conductor carrying a current at right angles to a magnetic field, and so, well, let's just say that's north and that's south, so by Fleming's left-hand rule, this side of the coil would go down and that side of the coil would go up. So now, that's the motor effect. Now, you have a conductor with a rate of change of flux linkage. So you will have an induced EMF, and because you have a current flowing, you will have an induced current as well. What I mean to say is, if we can have a current flowing to drive this motor, then there must also be a complete circuit, which means when we have this rate of change of flux linkage with my coil of wire rotating, sorry, I did the wrong way, this coil of wire rotating in the field, then we will have an induced EMF, and because we have a complete circuit, we'll have an induced current. Now, that current can only either flow in the same direction as this current, or in the opposite direction. Only one of those two things can happen. Now, picture it flowing in the same direction. So I put a current in here, which causes the coil to turn, which induces an EMF because you have a rate of change of flux linkage with the coil. which induces a current because we have a complete circuit. That current, if it flows in the same direction as this current, then increases the effect of this current, and so the coil turns faster, which means the rate of change of flux linkage is increased, which means the induced current is larger, which means the coil turns faster, which means the induced current is larger. You see where I'm going? In other words, if that was true, all I would have to do with my coil, forget the current, I just connect the coil up to, whatever. I connect it up to my, tarn, and I just give it a little tip. I touch it with my hand, I tip it. And so there is an induced current, which causes the coil to turn faster, which increases the induced current. Nonsense, right? That's a clear violation of the law of conservation of energy. You're getting something for nothing. That never happens. So clearly the current must flow in the opposite direction. In other words, the current must flow in such a way as to try to stop the coil from turning, which means, of course, in order to generate electricity, in order to induce a current, you must do work. Well, that makes sense. If I have connected this, let's now make this a resistor. If I've connected this generator to a resistor, when I drive current through the resistor, it's going to turn electrical energy into thermal energy. It's what it does. So if I'm not doing work, if I'm not putting the energy in to make the coil turn, where on earth is this coming from? So Lenz's law is a clear consequence of the conservation of energy. It has to be. There will always be the induced EMF induced in such a way as to oppose the change causing it. In other words, you have to do work to maintain this generating system. So you have two laws. You have Faraday's law of electromagnetic induction, that the induced EMF is proportional to the rate of change of flux linkage. And you have Lenz's law that says that induced EMF occurs in such a way as to oppose the change causing it. Why do we get an induced EMF? What's going on? Let's think this one through then. So let's say we have a conductor, AB, of length L, moving at velocity V through our uniform magnetic field B, flux density B. So in this conductor, it is a conductor because we have free electrons in our conductor. Those free electrons are charged particles. So now we have charged particles moving in a magnetic field. So let's use Fleming's left-hand rule. Our first finger, the field, goes straight into the page. Our second finger, well, our electrons are moving this way, which means our current is that way. So our second finger is now pointing to the left, which means the motion, the force on these particles is down. So we have F equal to BVE acting on these electrons. So electrons get shifted down. Now, of course, that causes an imbalance of charge. What you have now is a build-up of negative charge down here, and more work is needing to be done to move those electrons down here against that repulsive charge. So what you're going to get eventually is you're going to get a build-up of electrons down here, a lack of electrons up here. You have a potential difference. If you stop applying the force driving the electrons down, they will spread out again. there is a potential difference here. And of course, if you connect the two ends together, then you can have your current. So you've got your free electrons experiencing a force in the magnetic field because they're moving. That buildup of electrons at one end compared to the other causes your potential difference. And what you have is an electric field. You have this, so I want you to curly E. You have an electric field strength, V over D of course. And D is L in this case. The force on the electron is E times little e. That equals BVE. E is V over L. The E's are going to cancel. So our induced EMF, which we will call curly E again, equals BLV. So then we have another expression for our induced EMF.